This is section 2.3, linear equations. We've actually had to solve a few equations already, so we've done some of this. So some definitions. So I have a whole slew of definitions just so we can communicate with one another. So definition. A solution to an equation is a value which, when substituted into the equation, makes the equation true. And by value we mean number. So you may not think of it, but an equation is a mathematical sentence. It's waiting for you to give a value for the variable in order for you to determine whether or not it's true or false. For that reason, because we need a value to determine if the equation is true or false, they're sometimes called conditional equations. And the condition that makes it true is the solution. So we say that the solution satisfies the equation. Okay, so by making it true, it satisfies the equation. The set of all solutions of an equation is called its solution set. Now, we're giving the solution set to an equation. You have to enclose it, the value in braces. So, for example, if x equals 2, the solution set would be the set that contains 2. We usually don't concern ourselves with solution sets. We just say solve the equation or solve for x, something like that. So we prefer something that looks like this. Okay, very seldom have we been writing solution sets. A solution that fails to satisfy its equation is called an extraneous solution. Now, an extraneous solution is not the result of an error. You have done nothing wrong, and this number comes out, but it doesn't work. Okay, now, fortunately for us, we're not really going to see very much of that because we're going to be using our calculators in order to do most of our equation solving, and the calculators actually never do find extraneous solutions. To actually find an extraneous solution, you have to be solving the equation by hand, which we won't have much cause to do that. Definition. Equivalent equations are equations that have the exact same solution sets. Now, it doesn't mean that the equations are identical, because of course identical equations would have the same solution sets. But equivalent equations can look drastically different, but still have the same solution sets. As an example, x plus 3 equals 5 and 7x equals 14 have the exact same solution sets, namely the set that contains 2. So notice, these two equivalent equations don't look anything alike. Definition. To isolate a variable means to get that variable with exponent 1 and coefficient 1 on one side of the equation and everything else on the other side of the equation. Now, when isolating the variable, you're not allowed to have it appear on both sides of the equation. So if you have something like x equals 5x plus 13, x is not isolated because it's appearing on both sides of the equation. We want to get x all by itself on one side of the equation and not appearing anywhere else in the equation. So we'll be focusing on linear equations. In the next section, we'll actually be looking at non-linear equations. So this section is linear equations, and section 2.4 is going to be the nonlinear equations. So definition. A linear equation is an equation in which the unknown is only raised to the first power and does not appear as part of a denominator or special operations like roots and absolute values. So in some sense, linear equations are supposed to be the nice or simplest equations, but it turns out in the world of algebra, the linear equations actually are the exception to the rule of how you're supposed to solve equations. But they are meant to be the easiest. So our goal in solving equations is to turn the original equation, the problem that's given to you, an equation that looks like this: x equals a number. As soon as you're down to x equals a number, and if the number is a fraction that's been simplified, then you're done. Now notice in this, our coefficient is 1, our exponent is 1. Okay, so our exponent is 1, coefficient is 1. So in this one, the variable is isolated. So notice with a linear equation, to isolate the variable means you're going to get it down to x equals a number, in which case you've solved the equation. Now our goal in solving the equations, okay, even though it's to get it down to x equals a number, but based upon what we've got with our definitions, we can now precisely state the goal as we want to isolate the variable while maintaining equivalent equations. Okay, that's your real goal, to isolate the variable while maintaining equivalent equations. To accomplish the goal, we're going to need some equation solving principles. Now, there are several equation solving principles, but for now we're going to look at a couple of them. And they will actually do quite a bit for us in terms of solving linear equations. It turns out these two principles that we're going to look at are all you need in order to solve linear equations. So the addition principle. The addition principle states that if you have an equation a equals b is true, now a and b are not just simple a and b. I mean, a could be something like 5x plus 17 over 3, and b could be something like 11x minus 9 all over 12. So if you have an equation a equals b is true, then a plus c equals b plus c is also true for any value c. What the addition principle is really saying is you can add the same thing to both sides of an equation. Most time in algebra, if you're wondering, can I do this with an equation, the answer is usually yes, as long as you do it to both sides of the equation. The real question is that thing that you're doing to both sides of the equation, is it useful? Now, there's no such thing as a fraction principle. Now, some books will say that there is, but in order to subtract a number, you're really adding a negative. So we'll actually say stuff like, subtract 4 from both sides of the equation, but what you're really doing is you're adding negative 4 to both sides of the equation. Now, facts about the addition principle. Okay, first of all, it always produces equivalent equations. What that means is, assuming you've made no arithmetic errors, you don't have to check your answer as to whether or not it's extraneous. If all you've done is use the addition principle. Now, it's used to, number one, remove expressions that are added to or subtracted from the variable. Its second use, which is really the same thing as the first one but only stated in a different way, it's also used to combine similar terms. Like get all the x's together, get all the numbers together. That's what we mean by combine similar terms. So again, those two are really the same thing, just stated in slightly different ways. Now, the multiplication principle. Multiplication principle states that if a equals b is true, then a times c equals b times c is also true for any value c not equal to 0. Okay, don't multiply both sides of the equation by 0, because after all, 0 times anything is still 0, in which case you'd have 0 equals 0, which is always true, even if the original equation were absolutely false. So the multiplication principle is saying that you can multiply both sides of the equation by the same non-zero number. Again, don't multiply both sides by 0. Because you end up with this, which we know is true. Now, there's no such thing as a division principle, even though I'll say something like divide by 4. But division by 4 is really multiplication by a fraction. So if we say divide by 4, what you're really doing is you're multiplying by 1/4. Now, when we say divide, we really don't mean truly divide in most cases. What we really mean is write the fraction and reduce it. Now, if you're supposed to write a decimal, then yeah, you actually have to do the division. Now, facts about the multiplication principle. Okay, warning. It does not always produce equivalent equations. Now, fortunately for us, we're not going to encounter those situations where you don't get an equivalent equation. So we really don't have to worry about that. But if we were to look at algebra in all its glory, we would have to worry about when does this actually happen. And it's somehow related to, you're not supposed to multiply both sides of an equation by 0. So in certain situations, you have to check your solutions. Now again, it's not going to happen for us. So it says, I will let you know when you're required to do it. For us, basically never. Now it's used to, number one, remove expressions that multiply or divide the variable. Like if you have 5x, because remember, you want to have x equals a number. And the second use is really a cleverly disguised version of this one. It's used to clear fractions. What that means is you can make the fractions go away in an equation. Now, if the answer is a fraction, of course, it's going to come back. Excuse me. But while working with the equation, you don't have to be stuck with working with the fractions. You can, in fact, make them go away. Let's look at some examples. Okay, solve for x, simplify your answers, do not use mixed numbers or decimals in your answers. Now, the problems are going to range from the incredibly simple to the ones that are really just kind of hideous looking. So please do not be alarmed at the simplicity of some of them. There's nothing wrong with having a simple problem. After all, some people have been known to miss them. So here's our first one. X minus 9 equals 6. Okay, the idea is you're supposed to add 9 to both sides. So we need to add 9 to both sides. So here we are adding 9 to both sides. Okay, on the left, minus 9 plus 9 gives me 0, so I'm just left with x. On the right, you get 15. So x equals 15. So not overly difficult. Number 2. I have x plus 15 equals 9. Again, I want to make the 15 move to the other side, because that's what I was taught to say. You move it to the other side, and when you move it to the other side of the equation, its sign changes. So we're subtracting 15 from both sides. Whatever operation is being done on one side of the equation, to move it to the other side, you do the opposite. So I'm going to subtract 15 from both sides. Okay, on the left, 15 minus 15 is 0. I'm just left with x. And on the right, the 9 minus 15, I get negative 6. So x is equal to negative 6. Okay, I just get rid of this huge space that was there. It's kind of annoying to look at. Number 3, I have 3x equals 21. Okay, notice I don't have something being added to or subtracted from the variable. I got something multiplying it. So I got 3x equals 21, so I got to divide by 3. So remember, I'm doing the opposite operations. I've got multiplication by 3, so do division by 3. So we divide both sides by 3. On the left, the 3's are going to cancel. And on the right, 21 over 3, I get 7. So I'm going to get, as my final answer, x equals 7. So here we are canceling the 3's. Now, as time goes on, I'll say what I'm doing, like multiply both sides by 3 or divide both sides by 3 or add 12, but I won't always put in these messy details. Number 4, I have 5x minus 7 equals 18. Now, when you're solving the equation, you kind of do the opposite of my dear Aunt Sally. So we're first going to get rid of the stuff that's added to or subtracted from the variable, and then we'll do the multiplication principle to get rid of the stuff that multiplies or divides it. So I've got 5x minus 7 equals 18. I want to add 7 to both sides. I got subtraction on this side. I want to get the 7 away from the x, so add 7 to both sides. So I've got 5x equals 25. Right, 18 plus 7 is 25. Now I've got 5 multiplying the x, so I need to divide both sides by 5. Okay, on the left, the 5 over 5 will go away, and 25 over 5 is 5. So I get x is equal to 5. Number 5, I have 3 times 8x plus 14 equals 11. Okay, notice in this one I have an expression inside the parentheses. Now, according to my dear Aunt Sally, we're supposed to do the x plus 14 first, but we can't. They're not similar terms. So I'm going to distribute the 3. Okay, so distribute the 3. I'll have 24x plus 42 is equal to 11. Okay. Students usually call that drop the parentheses. Remember, the 3 affects everything that's inside the parentheses. Okay, now except for the different numbers, it looks like example number 4. So I need to subtract 42 from both sides. It's being added, so do the opposite, subtract 42 from both sides. So that'll give me 24x is equal to negative 31. And then I get rid of the multiplication by 24, so divide both sides by 24. Okay, on the left I'll get x, and on the right I get negative 31 over 24, which that's reduced, so there's nothing else we need to do. And that's your final answer. Now again, unless you're going to decimals, when we say divide with numbers, we really just mean write the fraction and reduce it. Notice going to a mixed number, going to a decimal, that takes a little extra work when you're doing it by hand. And if you had to go ahead and grab your calculator, well, that's still extra work. Number 6, I have 4x minus 12 plus 7x is equal to 3x plus 10. Okay, now when we're solving equations, we like to keep our equal signs all lined up, so that way you don't actually accidentally end up adding the same thing to both sides of the equation. Because notice on the left-hand side, I've got 2 x terms. So in order to solve this, the first thing I want to do is, on the left-hand side, combine 4x and 7x. Kind of like I got 4x raised, 7 more x raised, I got 11 of them. So 4x plus 7x is 11x. Then minus 12 is equal to 3x plus 10. So I'm combining the 4x and the 7x. Okay, I now have x's on both sides of the equation and numbers on both sides of the equation. Okay, I have a bias of moving the x's to the left, numbers to the right, though it doesn't really matter. So I want to move this 3x to the left. So I'll subtract 3x from both sides. I want to move this minus 12 to the right, so add 12 to both sides. So again, x is on one side of the equation and numbers on the other. Again, I like to move x's to the left, numbers to the right. So we'll subtract 3x and add 12. So I'm going to have, let's see, 11 minus 3, I got 8x equals 22. And now divide by 8. So I'm going to have x equals 22 over 8. which that will reduce. What, 11 over 4? So x is equal to 11 over 4. Number 7. Okay, I've got a problem that's just eat up with fractions. I've got 3/4 x minus 1/2 equals 7/8. Now again, there's no reason to work with fractions in an equation. I look for a common denominator for 4, 2, and 8. So my common denominator is 8. I'm going to multiply all of these numbers by 8, or if you want to, you can think of it as 8 over 1. Okay, the step that I'm doing now is called clearing of fractions. I'm multiplying through by the lowest common denominator. So I'll put in red what I'm multiplying by. Now you're going to do your canceling, like 4 goes into 8 2 times, 2 goes into 8 4 times, and 8 goes into 8 once. So if I look at what's left, now I'm not going to write denominators of 1. So I'm going to have 6x minus 4 is equal to 7. Remember, these numbers, these new numbers, all came from multiplying each one of these original fractions by 8. So if you really did multiply by 8, you'd have 24 over 4, which is 6. 8 over 2, which is 4. And 7/8 times 8 is just 7. Okay, now the numbers may be bigger, but at least the fractions are gone. Okay, this looks like something we've done before, so add 4 to both sides. And now divide both sides by 6. So I'll have x equals 11 over 6. So again, multiply by the lowest common denominator. Number 8. I've got 2/3 times 7x minus 8 plus 5/6 is equal to 5/4 x minus 4. Okay, I've got parentheses and I've got fractions. Now for me, anytime I see one fraction, I want to make it go away. When you're clearing your fractions, do not go inside the parentheses. So 7x minus 8 will remain 7x minus 8 until we finally distribute. Now I need a common denominator for 3, 6, and 4. Okay, it turns out it's 12. Okay, that's the lowest common denominator, 12. You're going to multiply every number that is outside parentheses by 12, including that 4. So we're not distributing, that's why the 7x minus 8 remains the same. So we're going to multiply everything by 12. Do not go inside the parentheses. So I've shown it in red. Again, we're multiplying every number that's outside parentheses by 12, including this 4. I didn't need to write 12 as 12 over 1 to do 4. Okay, now do some canceling. 3 goes into 12 4 times. 6 goes into 12 twice. 4 goes into 12 3 times. Okay, and now let's see. 8 times 7x minus 8 plus, okay, 5 times 2 is 10, is equal to 3 times 5 is 15, 15x minus 48. Again, all these numbers that are outside the parentheses, they came from multiplying each one of these numbers that are outside parentheses in the original problem, multiply each one of them by 12. Okay, now we're going to distribute the 8. So I'll have 56x minus 64. Remember, the 8 affects everything in parentheses. Plus 10 is equal to 15x minus 48. Okay, on the left-hand side, I can combine minus 64 plus 10 to be minus 54. So I have 56x minus 54 is equal to 15x minus 48. Now I want to move x's to the left, numbers to the right. So subtract 15x and add 54. So let's see, 56 minus 15, I'm going to get 41, and then the 54 minus 48, I get 6. So I've got 41x is equal to 6. Now divide by 41. So x is equal to 6 over 41. Problem number 9. I have 4 times 2x minus 3 is equal to 6x plus 2 times x minus 5. Okay, notice I've got parentheses on both sides. At least I don't have any fractions. So the first thing I'm going to need to do is I'm going to need to distribute that 4 and the 2 on the right. So I'm going to have 8x minus 12 is equal to 6x plus 2x minus 10. Now on the right-hand side, I can combine my two x terms and get 8x. So I have 8x minus 12 is equal to 8x minus 10. Okay, right now, some of you may be noticing something peculiar about this. Okay, I want to get x's to the left, numbers to the right. So I subtract 8x and add 12. So if I do 8x minus 8x, that's 0. It's not x. It's like I got 8 xylophones and someone took away all 8 of my xylophones. I have 0 xylophones left. So I'm going to have 0 equals, and 12 minus 10 gives me 2. So I have 0 equals 2. 0 never equals 2. This is a false statement. And notice, I've made no mistakes. So I've arrived at a false statement. Whenever you arrive at a false statement, that's no solution. Okay, so notice all the variables disappear, but not all the numbers. So if you get a statement that's clearly false, that's no solution. And by the way, when we start doing this in our calculator, if your calculator starts to solve an equation and it doesn't give you a number, but it just says false or false statement, that's no solution. Don't write false. It's not a true or false question. It's no solution. For number 10, I'm going to make a slight change to this problem. So number 10, I've got 4 times 2x minus 3 is equal to 6x plus 2 times x minus 6. Okay, I do need to distribute this 4, and I still need to distribute that 2. So I'm going to have 8x minus 12 is equal to 6x plus 2x minus 12. You know, just like before, on the right-hand side, I need to combine my similar terms. I got to combine the 6x and the 2x. So I'm going to have 8x minus 12 is equal to 8x minus 12. Now, some of you may be noticing something peculiar about this one. Again, if I try to get my x's on the left and numbers on the right, okay, I'm going to subtract 8x, I'm going to add 12. If I do 8x minus 8x, that's 0. If I do negative 12 plus 12, that's 0. I have 0 equals 0. Notice in this one, all the numbers disappeared as well as all the variables. So I've arrived at something which is true. It's always true. 0 equals 0 is always true. Whenever you arrive at a statement that's always true, that means the solution is all real numbers. Now again, if you were doing it on the calculator, when we actually start doing those, if your calculator says true, again, don't write true as the answer. True means all real numbers is the solution. Notice, except for numbers 9 and 10, all of our equations just had one answer. So, the pathological cases. Okay, examples 9 and 10 illustrate the two pathological or extreme cases in solving equations. If you arrive at a statement that is clearly false, like 0 equals 2, then that means there are no solutions. And that's what you write on tests and so forth. No solution. Don't say fault. It's no solution. Number 2, if you arrive at a statement that is clearly true, like 0 equals 0, then the solution is all real numbers, and that is what you should write on test, homework, whatever. Solution is all real numbers. Don't say true, it's all real numbers. For some reason, students tend to confuse both of these. Remember, if you get false, that's no solution. If you get something that's always true, that's all real numbers. Notice those things very seldom happen. It's kind of like any number you pick is going to work. How often does that really happen? Okay, word problems. A couple of word problems here to show you. Some examples. Number 1 says a car rents for $35.99 per day plus 89 cents per mile. So notice if you sit in the parking lot, it's $35.99 a day. Part A says use a formula to express the total cost C of driving the car M miles. Part B, find the total cost of driving the car 250 miles. Again, we assume you do it in one day. In question C, how far can the car be driven for $150 again per day? Round your final answer to the nearest tenth of a mile. So again, for B and C, assume that you do that in a day. So our solutions. in Part A, the total cost is the daily cost plus the mileage cost. Okay, remember the daily cost is $35.99. Now 89 cents, remember as a decimal, that's 0.89. So it's 0.89 for every mile you drive. So you're going to do the 0.89 times the miles. Remember, you're driving m miles. So the C is going to be 35.99 plus 0.89 m. There's your total cost. Question B. You're going to let m be 250, right? You're going to find the total cost 250 miles. So just replace the m with 250. So you're going to have C is equal to 35.99 plus 0.89 times 250. And of course, you would just take out your calculator and do the number crunching. You end up with a total of $258.49. That's the total cost for driving 250 miles. Excuse me. In Part C, how far can the car be driven for $150? Okay, round your final answer to the nearest tenth of a mile. So for Part C, I'm going to replace C with 150. So I have 150 is equal to 35.99 plus 0.89 m. So we have a nice little equation to solve. M is the unknown. Okay, notice m is on the right. I'm going to keep it there. So subtract 35.99 from both sides. So you're going to have 114.01 is equal to 0.89 m. Again, divide by 0.89. So 114.01 divided by 0.89, that's m. And you're going to round this to the nearest tenth, 128.1 miles. So to the nearest tenth, how far can you go on $150? 128.1 miles per day. My second word problem. Okay, Rip Me Off Rentals rents a piece of equipment for $5 for the first 3 hours plus 45 cents for each minute after the first 3 hours. High Cost Rentals rents the same piece of equipment for $6 for the first 3 hours plus 25 cents for each minute after the first 3 hours. Part A says express the total cost R charged by Rip Me Off Rentals for renting the equipment for m minutes. Question B says express the total cost H charged by High Cost Rentals for renting the equipment m minutes. And for question C, for what number of minutes do both companies charge the same total amount for renting the equipment? If necessary, round to the nearest whole minute. So our solutions. Okay, for Part A. Okay, the total cost again is the base price, this $5 for the first 3 minutes, plus the cost for minutes. So you got $5 plus, let's see, what is our cost per minute here? Okay, 45 cents. That's 0.45, and you're going for m minutes. So notice this is kind of like the car rental one to start us off. So R is going to be 5 plus 0.45 m. B, again, total cost is base price plus cost for minutes. So for High Cost Rentals, it's 6 plus 0.25 m. Now again, remember, these leading zeros, you don't have to write them. I just have the habit of doing it. And for question C, for what number of minutes do both companies charge the same? If they're charging the same, that means that R has to equal H. So for Part C, we want R to equal H and want to solve it for M. So going back, I had 5 plus 0.45 m is equal to 6 plus 0.25 m. That's going to be my equation. I'm going to solve that for m. Okay, I need to move m's to the left, numbers to the right. So subtract 0.25 m, subtract 5. So I'm going to have 0.2 m is equal to 1. Now divide by 0.20. M is 5. Remember, those are minutes. So the same amount for 5 minutes plus 3 hours. So for 3 hours and 5 minutes, because remember, both of them start you off with 3 hours, right? So remember, 60 minutes in an hour, so 3 hours is 180 minutes. So for 185 minutes, they'll both charge you the same. So you kind of like work fast. Okay, solving for variables in a formula. Now the formulas sometimes we call them equations. If it's all letters, that's when, or mostly letters, that's when we say formula instead of equation. So these are going to be equations that mostly contain letters. So solving for a variable in a formula is like solving an equation for its unknown. The variable you're solving for is treated as the unknown, and any other letter is treated as what were number. Now, what makes this confusing for a lot of people is that you feel like, well, I'm not doing anything with the letters. You're not. Like if I tell you to add a plus b, it's a plus b. That's all you can do. If I tell you to do a times 3b, it's 3ab. There's nothing else you can do. So a lot of times there's less work because you really can't do the work. So number 1 says solve PV equals nRT for t. Now please distinguish your capital letters from your little letters. So t is our variable. All the other letters are treated as though they were numbers. So again, we're starting off with PV equals nRT. Okay? So I want to get the t all by itself. Now I'm going to keep it on the right. Okay? I'm going to keep it on the right. So these other letters, the n and the r, they're numbers. If we had like 7t, we'd say divide by 7. So divide both sides by nr. So you're just going to write the fraction. I've got PV over NR is equal to T. That's all you can do. If I want to put the T back on the left, it's T equals PV over NR. Okay? So there's nothing else you can do because we don't really know any values for these letters. Number 2 says solve 5x plus 8y equals 3 for y. So I want to get y by itself. Okay, so the x is treated as what were number. So our solution. Okay, again, I got 5x plus 8y equals 3. Okay, I want to get y all by itself. So first, get rid of this 5x that's being added to it. So we're going to subtract 5x from both sides. Now, you really can't combine 3 minus 5x, so just leave 3 minus 5x. The left-hand side is just 8y. So I have 8y equals 3 minus 5x. You cannot combine these. It's kind of like I've got 6 oranges and I took away 3 apples. There's nothing else you can do. Now divide everybody by 8. So I'm going to have y is equal to 3 minus 5x over 8, or if you prefer, 3/8 minus 5/8x. Your choice. Okay, your choice. And there's nothing else you can do. As we do more of these, you might start to feel more comfortable with them. Now, there are some people that always insist before you, because this kind of comes into stuff we're going to be doing later on. We're going to be working with formulas and numbers at the same time. There are some people that say before you actually plug in the numbers, you first need to rearrange the formula to get the letter you want to work with isolated. You don't have to do that. Solving linear equations with the calculator. Now, we're actually going to see this in a lot more detail in section 2.4. We're actually going to look at a couple of ways to solve these equations with a calculator. Because in section 2.4 we do the nonlinears, and the theory for solving nonlinear equations is not very good. So we can use the calculator to solve linear equations. We're going to illustrate with an example. So we're just going to look at one illustration because we're going to see this in a lot more detail in section 2.4. And then after you see it, you can decide for yourself, would you rather use a calculator to solve the linear, or would you rather do it by hand? So here's our illustration. We're going to solve for x. We're going to simplify, no mixed numbers or decimals. Notice it's the same directions we had if we were doing it by hand. So here's our equation. 5x plus 1 is equal to 2x minus 7. Okay, so let's run through the steps. Let me get out my calculator since we're doing it with the calculator. Okay. Step 1 says enter the left side of the equation into y1. Okay, so let's enter the left side of the equation into y1. So y equals, and the left side of my equation is 5x plus 1. So 5x plus 1. Okay. Step 2 says enter the right side of the equation to y2. Okay, you can press enter after entering the left side of the equation to y1 to get to y2. Okay, so let's go back to our calculator. Okay, I'm still at y1, so just press enter. You could have used the arrow keys as well. So the right side is 2x minus 7. 2x minus 7. Okay, if you're done, we are done entering the equation. So when you're done entering the equations, you can quit the screen if you want, or go to whatever the next step tells you to do. So this is the left side of the equation. This is the right side of the equation. Of course, you can reverse the two if you want. Always just put y1 as the left side, y2 as the right side. Okay, step 3. We are wanting to perform a calculation with these equations. So press second trace. Okay. Now second trace is actually calc. Okay, so C-A-L-C. We're wanting to do a calculation. That's what the C-A-L-C stands for, a calculation. So second calc. And you have these choices. Okay, you have these choices. 6 and 7 are for calculus. 3 and 4 we'll do later on. Number 2 we will also do in section 2.4. So we're wanting to find out where y1 and y2 intersect. Because I'm wanting to find out where they equal. So step 4, we want to find where the two equations intersect. You can scroll down to choice 5 and press enter, or simply press 5 itself from the keypad. Now be aware that the calculator is going to start to graph each equation. If you do not see the graphs, you may need to zoom out. Okay, so when I pressed 5, okay, it's starting to graph them. Remember, y1 is in blue, y2 is in red. Okay, so this screen should look more or less like that one. Now notice it's flashing at y1, which is the blue curve, and it's telling you that y1 is 5x plus 1, which it is, because it's asking you, is that the correct formula for the left-hand side, for y1? So if our first curve is correct left-hand side, just press enter. And then after you press enter, it's going to have a flashing cursor on the red curve, and it's asking you, is the red curve, is it 2x minus 7? It is. So you press enter again. So let me get caught up. So my first curve is, in fact, 5x plus 1. Okay, now it's jumped down to the red curve. Is it 2x minus 7? Yes, it is, so I press enter. Okay, now it's asking you for a guess. Okay, asking you for a guess. So step 7, the computer is asking, or is now asking you, it's actually the calculator, if you would like to start with a guess of x equals 0. Okay, it's as good a guess as any. Okay, if you want to change the guess, fine, but I see no reason to not change the guess. So basically, after you've gone choice 5, you're going to press enter 3 times. That's really what's going to happen. Okay, so let's press enter again. Okay, and it's given me this. Okay, so I've caught up to this screen. I've got x is negative 2.6667, something like that. You don't care about the y value. You don't really care about the y value. So that means that x is negative 2.666, so on. Okay, again, ignore the y value. Remember, we were told no mixed numbers or decimals. So what are we going to do? To change the x decimal to a fraction. Okay, so we're going to follow these steps. So remember, I now know my answer. So I can quit the screen. Just do second quit. Step 1, we need to get x into the home screen. So quit the graph screen by pressing second mode. Okay, so you should be taken back to the home screen, which I was. Okay, press your x theta t key, xt theta n key and press enter. It gives you the value of x. Okay, it gives you the value of x. So I press x and enter. Remember, you want this to become a fraction. So remember, that was math, enter, enter. Your answer is negative 8/3. So that's what's happening there. So press math, then press enter, and it's telling you it's going to change the answer to a fraction, and then press enter again. Okay, now you can see if the equation is incredibly simple, like x minus 9 equals 12, to go through all this would be painful. But if you have a really nasty equation that you're looking at and you just say, I don't want to try to solve that, then it might be worthwhile to let your calculator doing it. Now, in section 2.4, we're going to discover that what we just did is called the crossing graphs method. Okay, section 2.4 will look at 2 different ways to have the calculator solve an equation. Now, in section 2.4, we look at nonlinear equations, and we'll really have no choice but to use the calculator. So for now, for section 2.3, it's kind of your choice. So the solution to 5x plus 1 is x equals negative 8/3, just like it says right there. Again, you can decide for yourself if it's worth doing this way. Now again, for linear equations, even though I know this method, I very seldom use it. If it's nonlinear, we really have no choice but to use it. So we'll see this in a lot more detail in section 2.4. Now if you get an error statement, you have to zoom out. We will actually have some of those when we start doing the ones in 2.4. Okay, so that way you can see how to deal with them. So much for section 2.3.